When converting to a z-score, a score that was once one standard deviation above the mean will remain that way. Changing it to a z-score is simply transforming it to an equivalent number in a different sort of language, that is standard. As I show here, a score of 60 is one standard deviation above the mean of 50, when the standard deviation is 10. The z-score would be converted to 1 and remain one standard deviation above the mean, which is 0. As you can see, the tables only show the positive numbers. That's because their negative equivalents are simply that, equivalent. Any normal distribution can be taken and viewed as a standard normal distribution with a mean of 0 and a standard deviation of 1. This serves as the basis for most of our analyses. Values along that distribution are referred to as the scores. A z-score represents a number, the number of standard deviations an object is above or below the mean. Using the same sample, we could compute a z-score for 43. Let's plug it into the equation, where z equals x minus mu over sigma. X equals 43 and mu is the mean, divided by the standard deviation, which is 10, giving us a z-score of negative 0.70. So now we'll ask what the probability is that there will be a score more than one standard deviation above the mean, and what the probability would be one standard deviation above or below the mean. We can look at the shaded portion with the percentage written here, 0.1587, which refers to about 15.9 or 16%. 16% is the probability that there will be a score more than one standard deviation above the mean. What do you think the probability that the score will be more than one standard deviation above or one standard deviation below the mean? In this case, we would simply add the portion above one standard deviation and the portion below one standard deviation, leading us to approximately 32%. As we look at the z-table, we can see how much information it gives us based on the z-score. Look down at the z-score of 1 and see that the percentage represented between the mean and one z-score, or one standard deviation, is 34%, or 0.3413, just as before. Try calculating the probability that someone will score between a 70 and 95 on the first exam, assuming the scores are normally distributed. Scores can be used to determine probabilities. We may wish to determine what the likelihood is that a score will fall within a given range. That's where limits come in handy. If we are looking for the limits within which 95% of the scores fall, or the interval, if you will, that means that it would be useful to understand the limits beyond which the remaining 5% of the scores fall. We can find a z-score that cuts off 2.5% at each end or tail of the distribution. Here we see that limits can be set up using the mean of 50 going both ways, using one standard deviation as a z-score. We see that 1.96 times 10 shows that the scores will fall between 30.4 and 69.6, 95% of the time. Using this formula, we can convert a distribution with any mean and variance to a distribution with a mean of 0 and a standard deviation or a variance of 1. We can refer to these transformed scores as standard scores. The process of this transformation is called standardization. Note in the text box that once we have a raw score converted to a z-score, we can use it to compute the probability that any observation will fall within a given interval. Next, we look at the probability using the analytic view. Imagine that you have a bag of M&Ms in front of you and you haven't eaten them. And you reach in and pull one out though. To the right of the slide, you see that there's a distribution of the colors in an average bag of M&Ms. Keeping that in mind, assume that there are 100 M&Ms in the bag. What then is the probability that you will pull out a yellow one? Because